Good morning, everyone, and thank you for joining our webinar on how to optimize boiler-based power plants. Before we start, I would like to show you some practical information. So the webinar will last approximately 1 hour. It will be recorded and we will share with you the recording afterwards. Whenever you have questions or suggestions, you're welcome to use the chat function on your control panel. And when the presenters are done with their presentation, then you will all be able to unmute yourselves. A little bit about the presenters. We have Stine Hvid, Head of Training, and Lars Illegaard, Engineering Specialist. They're both worked more than 30 years, both for boiler-based and engine-based power plants. And I will now give the floor to Stine.
Yeah, hello, good morning. The agenda for today is optimization of efficiency, intelligent monitoring of the plant, reduction of plant-owned consumption and consumables, combined heat and power, CHP, plant availability, lifetime extension of plant and equipment, and plant surveys. First, our history in short, it dates back almost 180 years, back to 1843, where it starts as a humble machine shop in the central part of Copenhagen. The company have evolved over design and building of large diesel engines, ships, shipyard, large power plant boilers, complete power plants with boilers, engines, up till today, where BWSC focus on long-term operation and maintenance contracts and provision of all kinds of services to power plants within all technical disciplines. We have over the years been operating worldwide with engine-based power plants in a broad belt around the equator on islands and remote areas. Boilers are concentrated in around Europe, but also some in Asia. We are operating power plants in Europe and Asia. Our topics and our services supports United Nations Sustainable Development Goals for affordable and clean energy, industry, innovation and infrastructure, sustainable cities and communities, responsible consumption and production, climate action, and partnership for the goals. But plant performance optimization, why bother? Simply because high plant performance ultimately will cause you less trouble. We all know that sometimes it's all firefighting, stress, but trying to keep focus on optimizing the performance can give you a more relaxed approach to operation and maintenance of your plant. And maximizing the production output, lower the maintenance costs, reduce the emissions, which gives a green profile, better financial results, and ultimately satisfied plant owners and end users. Efficiency optimization. Many factors affect the efficiency, such as fouling of boiler and heating surfaces, blockage of flue gas passageways, condenser fouling, condenser performance in general, vacuum leaks, vacuum ejector performance, steam leaks, external as well as internal, and especially internal steam leaks in boiler and turbine are difficult to find. Air preheater fouling. Air-cooled condenser In addition to fouling of the condenser, also inert gases in the steam will accumulate in the condenser and needs to be removed continuously by the ejectors not to block heat transfer. Thermal imaging or infrared camera is an effective way to detect cold spots like this. It's not uncommon to see dead spots in corners, but keep an eye on them to see if they are growing. Sometimes it's a design issue, but again, take these thermal images on a regular basis to check that these areas are not growing, indicating leaks or insufficient performance of the vacuum ejectors. Another way to improve the boiler is online cleaning. It has shown that during soot blowing of a boiler, soot blowing in one way of the soot blower lands will remove almost all the soot or deposits on the tubes. So moving the lands inwards with a minimum amount of steam and then full blow on the way out will remove almost or most of the deposits, but save steam. For saving steam, producing more power or more frequent soot blowing. In addition, the reduced soot blowing will also reduce the erosive wear on the boiler tubes. Upgrades to one-way soot blowing regime will require a pre-investigation, installation of a control valve, and modifications in the soot blower controls. When burning more nasty fuels, hard slag deposits tend to build up on the tubes, leading to hot corrosion, higher local velocity of the gas, increased erosion on the tubes by the fly ash, resulting in thinning of the tubes and eventually risk of tube failures. If the soot blowers are working correctly, but steam soot blowing is not sufficient to keep the tube bundles clean, then a mean could be micro explosive or blast or band cleaning. Then intelligent monitoring of the plant, and I'll leave the scene to Lars.
Yeah, hello. When looking at plant performance, then a condition to be able to optimize is, of course, first to know where are the performance. And then, of course, one should primarily look for any negative trends. However, for biomass boiler plants and also waste to energy plants, this is not as easy as it sounds, because often such plants are run with full boiler load. They are not obliged to participate in load adjustment on the grid. So maximum is to keep the boiler busy at all times at full power. Unfortunately, then the electrical output is a side product, and it will vary according to conditions. So you don't have a steady electrical output to judge the performance. And there are several reasons why the electrical output will vary. One, particular for biomass and waste, is that the fuel is not homogeneous, and also the fuel feed is a bit uncertain, density of the fuel. You have a combustion delay between feeding and actually getting the heat out of the fuel. And often also the grate has an on-off operating mode, and all this contribute to disturbances. And then on top of that, Mother Nature provides an ambient temperature which affects the back pressure for the turbine, And then again, you have a dependency on the electrical output. And if there's heat export, this will of course also affect electrical output. If there's variation in the heat export, it will affect electrical output. And there are other minor factors that will also introduce disturbances. And in most plants, it's a classical DCS system where you do get a lot of measurements, for example, the electrical output and the ambient temperature, but it varies. And then the big question is this good or bad? Then one ought to do some processing of the direct measurements to calculate or present some performance indicators which are better to tell the status of the plant, and then kind of lifting the fog of information and get a clear picture of performance. And ideally, one should have a model running in the background, continuously predicting what should the result be on, for example, the electrical output, and then you could see, is my result here or below? This is, however, quite ambitious and not very practical, because models are software packages with license and so on. But in reality, one can get nearly there in a much simpler way. And one way is to go back to the construction phase or EPC phase performance test procedure, because there you have this need, in order to demonstrate a guarantee, that you need to operate the plant at whatever conditions are there, and then judge whether you are in a good position or not. And this would typically look like this. It could have different format depending on the EPC and the contract and the owner, but the principle is that you measure something and then you apply a correction factor which depends on a lot of circumstances, and then it will bring the measured result to a reference condition which is supposed to be stable. And in a performance test, then one would look at, is it equal to or even better, larger than guaranteed? Then there's good reason to be happy. If it's lower than, then of course not so happy. And if we take an example, here we have a performance chart from a model-based estimation of a plant, and then the curves here symbolize how the electrical output vary with ambient temperature as main parameter, and the different curves are different level of heat export. And actually the heat export here up to 15 megawatt, the example is a nearly 80 megawatt boiler, so it's not a dramatic heat export, but one can see has a significant impact on electrical output. And the overall variation from these two parameters alone are from nearly 32 megawatt to 26. So it's a span up to 6 megawatt or 18% variation. Most of it related to heat export and some of it to temperature. And one could also choose to plot it in an alternative way where it is the heat export that's the main parameter and the curves are then ambient temperature. And as one can see, and also as expected, pulling heat from the circuit hurts electricity. And we'll come back later to the slope of these curves, but it's obvious that they're not completely straight. So one needs a fairly accurate procedure to predict accurately what circumstances should result in. And then one have to notice that an EPC correction procedure typically assume that the boiler is run at full load because that's the nominal condition of the plant. But in reality, it is quite common for inhomogeneous fuels to see boiler load fluctuations or dips in output, which are actually very difficult to prevent. It's kind of inevitable with the conditions. So this is not really a plant performance deficiency, it's just a disturbing factor confusing the picture. And therefore, often one have to add an extra term to the EPC correction procedure, where the first correction to a reference condition need to be adjusted to a nominal boiler load. That will further stabilize the estimation. Of course, one should still be interested in fluctuations and try to minimize them, but it's a good way to take them out from the measurement. And of course, the heat input to a boiler is not a very well defined or measurable thing, but if one instead look at the boiler steam production, which is online measured, then one can substitute this with nominal steam flow versus the actual and get very close to this correction. And if we take an example, here we have a typical DCS measured electrical output. It's over a period of 2 weeks, and one can see that there are quite significant variations in the output picture. It goes all the way from 23 megawatt up to 28. It's the same, roughly 6 megawatt we saw in the other. And when one look at this, it's difficult to see, is this good or bad? The factors that produce this scatter of result is several. One is that the ambient temperature, the blue curve here, of course, has a tendency to vary in a daily cycle, cold in the night, a little warmer in the day. And then on top of that, there's the brown curve here, which is the heat export. It is not varying so much, but it also has some daily cycles with more heat in the night when it's cold and less in the day. And then on top of it, there's soot blowing, in this case, once every day. And the steam flow from the boiler also varies a little. And all this affects the measured output. And of course, one can look at this and say, okay, all the dips here, they can be matched up to the soot blowing. But as we can see, it doesn't dip to the same level. So we know why, but exactly if it is good or bad is difficult. We can also see the daily cycles here and say, okay, it's the temperature primarily. But in this case, the heat export is actually opposite, that in the night when temperature is low, which is good for electricity, heat is a bit higher. So it's the net effect of two opposite disturbances. And then the idea would be to try to straighten out this signal. And if we start with the full load correction, we come from the blue one, which was the same as before, to this brown one. It's not impressive. The spread is more or less the same, but if we look into details, we will discover that the dips here are no longer aligned with soot blowing completely. Some are, but there are also some gone. And the daily cycles are less pronounced than up here. They have been smoothed a little. And if we then continue with this extra load correction or steam flow correction, then actually something dramatic happens. We get to this gray curve, and of course there's still some fluctuations, but now it looks like a straight line. So this would be the one to monitor. In this case, it's only 14 days, so of course one should not see any significant deterioration of the plant in 14 days. But if this is looked at monthly and annually, then maybe one can detect a trend which need to be addressed. And then, of course, this example was only the main output, electricity. And if one detects something, then of course it's nice to know, but you don't really know where in the plant the problem is. So it's only a first step, the first warning light that there's something wrong. Then next level would be to split up the plant in subsystems and main equipment, and then do something similar for these systems, so you get a more direct indication that the problem is in one place and not elsewhere. And just to take examples, it's possible to calculate the steam cycle efficiency and refer to reference conditions. And then one can actually get a picture of the turbine itself, degradation, leaks, or whatever, before it is seen at plant level. And it will then not be disturbed by the condenser or the boiler. It is carved out as a steam cycle. Another possibility is to look at the air-cooled condenser separately, by simply having a model running and predicting what should the vacuum be with load and temperature and so on, and then compare it to what it is. And then one could get a signal on the ACC separately. Boiler fouling is an obvious one also, and if it is corrected for load, this could give a good signal. Where are the fouling level? Is it under control, or do we need something extra? And to take some more examples, the ID fan is a good one to look at, ideally corrected for load, and then look at the speed. And if there is a tendency that the fan speed increase more than can be explained, then it indicates some fouling in the flue gas path, or maybe a filter bag clogging or something similar. So again, one can better pinpoint the problem. Also, steam turbine extraction temperatures are good to look at, and again, best with a correction to reference conditions, because then if something happens inside the turbine, there would be an early warning in extraction temperatures. And as everyone knows, it's difficult to look into the turbine, but this is a way to take the temperature and see if there's something to look further into. And this is only examples, and one can continue and try to carve out more and more systems and try to get a clear picture of where the problem is. But of course, one had to stop at some level, because this could be an endless exercise. And in general, when doing this processing, then of course the goal is to get some indicators that either produce a straight line when things are okay, or show a picture of a trend where some action brings it back, and then one can use it for scheduling actions. And just to take one example of subsystem monitoring, then we look at an air-cooled condenser. And typically the performance of a condenser, as it is informed by a manufacturer, is in the form of a performance chart, where the condenser loading is the x-axis here, in this case as steam flow, but that's the same as heat load. And then there are different curves for ambient temperature, and one can go in with a load and a temperature and find what should the back pressure for the turbine be. And we can immediately see here that even running at full load, which has a tendency to follow a slightly tilted line, then you can have anything from 200 or more millibar if it's very hot, down to around 50. So there's a big range here. And also if you have load variations or heat export, and even with the constant temperature, you can also have a significant variation in the back pressure. So this only illustrates that it's difficult to know what should the back pressure be if everything varies simultaneously. The trick is then to make a model of the condenser, and it could look like this. This is a structured model which can actually reproduce more or less all air-cooled condensers. And it looks a bit nasty, but at the end of the day, it actually only relies on very few parameters, and some of them are not very important. You can actually guess them without much significance. And then if this is programmed into the DCS, it would follow a model here where we can see that the dots are read from the manufacturer performance chart and the colored lines are the model, and it's able to predict all sorts of performance conditions. And even if you speed down fans, which is sometimes the case in the winter, it will also come up with quite accurate prediction. And if we look at the application of this, then this is a typical picture over a summer period from May to September, where either the recorded pressure or temperature, of course, varies, both short-term and also long-term, and they are more or less parallel because temperature and pressure is interconnected. And when one look at this, of course, it's higher here in the good July, August period, and it's lower here, but is it as expected or not? That's a bit difficult to see. If one then apply the model, and it can be either applied on temperature level or pressure level, then certainly one get curves like this. And here it's now the deviation between what the model says and the reality says. And now we can see a clear trend that the condensation temperature tends to creep up, and certainly it drops, and it happens to be a wash of the condenser here, and then it more or less drops down to starting point and then starts climbing again. So this is an efficient way to find out when to set in with a boiler wash. One can simply define a maximum negative deviation and then say every time I breach, say 4 degrees, then better start preparing for a wash. So this can save some performance and also, of course, help not washing too often, because then there's a water consumption and so on. So it's a good optimization tool. And then just some other quick examples. Then the steam cycle efficiency, which was mentioned, and that's this brown curve after processing becomes quite straight. And there's also variations in ambient temperature, a little in heat export, and even the boiler load is running up and down. But the result of an efficiency model is a straight line. And if it is not straight, then there's a good reason to look for something in the turbine condensate circuit. Another one is this with boiler fouling, where pressure or vacuum is measured over different sections of the boiler. And then one again see here a trend, like for the ACC, that and this is a long period, it's more than a year actually, So there are lots of soot blowings here, but the soot blowings are not able completely to clean the boiler section, so it builds up and pull the pressure drop down or the vacuum, and then boom, and this is actually a blast cleaning, and then one comes back, and then it starts good period, and then creep again, and new bank cleaning, and then so this is again an example where one can get keep a good eye on the boiler and find out when is it time to do this extra effort of cleaning out. The last one is a bit special. It's a high pressure bypass valve where there's a de-superheating valve dosing condensate which could leak and then harm the process. And this can be seen here by comparing two characteristic temperatures, and the drop of this one actually signifies increased leak. Then there's been an outage and a repair of the valve, and then boop, up again, and then unfortunately again it starts, then a new short stop and a repair, and apparently here it looks like it was a better repair because now it seems to stay tight. And then it is back to steam for a period.
Reduction of plant own consumption and consumables. Yeah, there are a lot of potential savings, and to realize them, formalize a regular check for leaks, small adjustments, unnecessary use, excessive consumption of, among others, electrical power, steam, dimming water, compressed air, consumables, abatement chemicals. Probably, yeah, make some trends, and also consider tariff optimized consumption if possible. So do steam blowing and other large consumptions outside the peak hours or peak periods for high electricity prices if possible. That's a way to save consumption. Also consider own power consumption of admin buildings, workshops, warehouse, fuel storage, etc., which are often forgotten. Even though some of these potential savings seem small, adding them up can amount up to considerable sums. Some low-hanging fruits examples: review the control concepts to check if there are any unnecessary operation of pumps, fans, compressors, etc., and adjust to only demand-based capacity control. Air conditioning or building heating systems. Check the condition, check insulation of pipes and insulation of buildings. Timers on air conditioning or heating to save power, especially at night and weekends where no one are present in offices and other places. And it's a way to save power. Shift to LED lights if not already installed, indoor and outdoor. It saves up to 80% power. And the lifetime of LED light is up to 10 times the lifetime of other traditional lamps, meaning it saves manpower to replace the lamps. Motion sensors on lighting, so lighting is just not turned on unnecessarily. And to harvest this, initiate a thorough systematic plant survey to reveal potential savings and improvements. Another way to save some power is to check for flue gas pressure loss and hence electrical auxiliary power. The flue gas path from boiler to stack by a treatment facility is often complex and consists of large duct dimension. Ducts can be round, square, rectangular, or often a mixture. Flow resistance in ducts is affecting the ID fan, meaning that if there is more resistance, then the ID fan takes up more auxiliary power, and it costs. Large dimensions of ducts does not invite for nice and soft bends, so sometimes we see sharp bends in the duct system. So review the flue gas path to identify unnecessary pressure loss, and that can easily be remedied to save power on the ID fan. And if we save power on the ID fan, then we also increase the ID fan capacity reserve. In this example, there is a sharp bend in a duct, and just after the sharp bend here, the separation zone creates some vortex turbulence, and that is restriction because we have a restriction which causes a high velocity. In this example, the flow resistance coefficient is 1.2. But if some guide bands are welded in, and that's pretty simple, then the separation zone will be significantly reduced, meaning that the restriction is reduced. And the flow resistance can be half. It is possible to further improve the flow by rounding the corner here. That requires a little more work, removing insulation, cladding, etc. And a numeric example on a store-fired boiler, 120 megawatt thermal input with flow velocity at 20 to 25 meters per second, and calculation of pressure drop and power on ID fan. With a sharp bend, the pressure drop is, in this example, 202 Pascal. With improved bend, we can halve the pressure drop, meaning the power to the ID fan is also half. If we take the saved power, in this case 9.6 kilowatt, and multiply by 8,000 running hours per year, then it gives 76.8 megawatt per year. We assume an electrical price of 100 euro per megawatt hour, then we can save almost 8,000 euro per year. In this example, 20 meters per second, if we are talking about 25 meters per second, the difference is even bigger, and we can save up to 12,000 euro per year in this example. That's a pretty simple measure to reduce the own consumption. Payback time in this case are rather attractive. And there is no way around it. We must all reduce our climate footprint. In addition to savings, an efficient way to reduce the emissions from a power plant is to optimize the overall plant efficiency by harnessing as much of the excess heat as possible for export combined heat and power. There are a lot of well-proven technologies for combined heat and power, or CHP, on the market. Many Nordic countries have been utilizing and refined these processes for decades. By using both the heat both for power production and export of heat, then the carbon emissions can be reduced by optimizing or utilization of the fuel. And the simple concept of CHP conventional system is that we have a thermal power plant producing power, and all the heat is just dissipated. Heat is produced in a boiler for heat, and that utilizes the fuel in total by about 50%. By combining the heat and power production, then the total efficiency or utilization of the fuel can be lifted up to 80, even 90%. So back to Lars with more details.
Yeah, if we are to look at the combined heat and power potential, then we could start looking at the energy flow in a typical boiler-based power plant. And it would look something like this, that we put in a certain amount of fuel, which we define as 100%. And then through the boiler, we lose something with the flue gases, 6 to 7% if we release at 130, 140 degrees, and a little as radiation and ash losses also. But we do get around 90% of the energy out in the steam cycle. But then unfortunately, Carnot has defined that you cannot get all this to mechanical or electrical power. It's only around 40% which can be converted into mechanical energy. The rest goes as exhaust steam, which needs to be condensed. And in this case, after some additional losses and own consumption, you typically end up in the lower part of the 30% electricity. So not a very impressive efficiency. But then in principle, one could take the entire stream of exhaust steam and condense it against a heat carrying source to export as heat. But it does have some consequence on the electricity, and as a rule of thumb, if you condense at 10 degrees higher than you otherwise could, will cost you 3% on the electricity or 1% in efficiency. So going from around 35, which would be typical for an air-cooled condenser with normal weather condition, to 85, so it could be used for district heating, that's up 50 degrees, then electricity will drop 15 or 5% on efficiency, but you then get 50% extra heat. So the total efficiency will increase and approach 100. And then there's actually another possibility, and that is to take the exhaust gas, and if we cool this, we can harvest extra energy, and if we cool it enough, we can actually also utilize latent heat of the water content in the fuel and the combustion water, and even further increase output, and then actually end up with a total efficiency of more than 100%, which is of course because we don't count this as the 100% input. And if we look at the various plant couplings, then this one would be the first one, electricity only, boiler, turbine, and condensing against the surroundings, in this case air-cooled condenser. But then if one wants to go for the full heat potential, one would condense against a condenser, exporting heat as hot water, or even taking out the exhaust steam and export that. And then one come from these some 30 something to around 90 with a moderate loss of electricity. The only problem here is you have a fixed ratio between electricity and heat output. So this would typically be for waste incineration plants where the main goal is to burn waste, deliver some heat, and then get the electricity, but you cannot vary. But then fortunately, there's also a hybrid solution where you still condense some of the steam at as low as possible, but you take out extraction steam either for producing hot water or directly as export steam. And this concept has the advantage that you can actually vary between electricity and heat. So, for example, making more heat in the winter and then in the summer, when the demand is low, you make as much electricity as you can. Unfortunately, this is actually options at design level, and once the turbine has been chosen, it is born for one or the other concept. So you cannot just choose full condensing, back pressure condensing for a turbine that was originally for full condensing. So in most cases for existing plants, it is the third option to have a partial CHP utilization by taking out extraction steam. And of course, it depends a little on the turbine how much you can take out, because it is designed for something. And then if we look at where to take out the heat, of course, the further up you take it, the less expanded it is. So it is an advantage to take it out as far down in the turbine as possible. And that's what is illustrated here for a medium boiler starting at 80 bar, 480 degrees. And if you expand through the turbine, temperature will drop with the pressure, eventually hit the saturation curve and then follow that, and it becomes a two-phase flow, steam and condensate. And if we start up here, one could, if we expand all the way, harvest a little more than 1,000 kilojoule per kilo steam as electricity, or we could take it out and get more than 3,000 kilojoule heat, but of course not both at the same time. So if we take heat up here, it will cost about 1/3 electricity. And this ratio is fairly constant, some of a long way here, but in the end, if we took out the steam at the back end, it doesn't cost any electricity, but still has a heat content. And this can be shown like this, is usually called Z factor, which is the blue one. It is how much electricity does it cost to take out 1 megawatt heat. And it starts at around 1/3 and then gradually becomes less and less. One can also reverse it. So it's kind of an exchange ratio that in the beginning you can get 3 units of heat for 1 unit electricity, but in the lower end it becomes much better. You can actually get 10 times more heat if it is at a low temperature than you lose in electricity. And if we take a business case example, then let's say that there's a heat client next door and he would like some steam at 8 bar, which is a saturation temperature of 170. Then the Z factor or electricity cost factor would be that you lose 1/4 of a megawatt hour electricity for each megawatt heat exported. And if we assume we have an electricity tariff of €100 per megawatt hour, then the energy price or the revenue loss of 1 megawatt heat would be €24 per megawatt hour. And then that's only the energy part. Of course, one needs to sell it at a slightly higher price to offset capex and also hopefully end up with a little profit. But if we then compare to the client and say, what if he had to raise the steam on his own with a steam boiler, efficiency 90%, then he would need to find oil at a price of 250 euro per ton to match this energy price. And at the moment, Rotterdam oil price is of the order 600 euro per ton. So of course, it would be much better to buy the combined heat rather than make your own. It could also be converted into natural gas, but it's more or less the same, that it ought to be an attractive price. If we look at another example where we have a client requesting hot water, it could be a district heating system, but it could also be a large industry needing hot water for building heating and okay with 90 degrees. Then the electricity cost is only half of this, and then it ends up, of course, that the sales price or minimum sales price is even more attractive. And if the neighbor cannot find oil at 110 euro per ton, then he should buy here. And if Rotterdam is 600, then a very attractive price. This is only examples because unfortunately each country have their own tariffs and taxes and so on. So one have to adjust this to regional conditions. But usually it does give an attractive price and potentially a good business case. If we look at the other option, this exhaust gas low temperature milking, this is a bit different. It doesn't cost anything on the electricity. On the other hand, it's a more costly installation. But it would typically look like this, that you add a loop to the existing flue gas path, taking out the flue gas at around 130, 140 degrees, and then start injecting a lot of water to quench the flue gas, and it then ends at a temperature of around 60 degrees, which can then be cooled in a scrubber. And the first step here would be, if you have district heating with a low return temperature, you take out some heat directly, maybe end up at 50 degrees here. And if you want to go further, you could cool indirectly to maybe 30 degrees here, but it would then require a heat pump to work up the temperature level to district heating or hot water. And of course, all this depends on the flue gas condition and eventually how wet the fuel is. If we look at temperature conditions, then one could of course take the flue gas at 130, cool it in a dry cooler or economizer, and extract around 3 megawatt, and with the ability to actually heat water to a good temperature, but starting from low. But the real benefit is in the condensation, and it comes here, so you can actually extract a further 5 megawatt, still with water of a temperature of around 50, and you cannot go much up in forwarding temperature, but it's much simpler to go directly down here, quench it, and then cool it. And this was only with wood with 25% moisture. If the fuel is even more moist, like virgin wood could easily be 40%, then you can actually harvest a lot more. And of course, if it's dry, less. So it all depends on the fuel. It has to be evaluated for the condition. And then we are back to Sten again, I think.
Yes, combined heat and power, improved energy utilization. The Heat can be used for industrial and or district heating, CHP, industrial and or district cooling, meaning the heat is converted into chilled water by a heat-driven absorption chiller. The benefits are obvious: less impact on the environment, greener profile, reduction of overall fuel consumption, and potential additional income for sale of heat or chilled water. There are many possibilities. We have a combined heat and power plant, exporting heat for building heating, industrial heating, and or by a absorption chiller, produce chilled water from the hot water into industrial consumers or housing, cooling, air conditioning. And there are a lot of possibilities: distilleries, breweries, cold stores, refineries, office complexes, shopping malls, hotels, airports, hospitals, vertical farming, greenhouse, etc. So look around your plant for potential off-takers of heat and or chilled water. Yet another way to improve the efficiency and optimize the plant is to look at the availability factor. Maintain a high availability by close monitoring and trending the plant performance to schedule proactive maintenance and minimize forced outages. Focus on optimizing maintenance planning and preparation. Quality control programs for maintenance work, so the plant doesn't have to come down just after startup after maintenance due to poor maintenance. Keep relevant strategic or safety spare parts available on site to prevent long downtime waiting for parts. See to that the fuel is correct quality and the water is treated well according to the quality requirements. Lifetime extension of plant and equipment. Boilers, turbines, and other equipment last, if well maintained, often longer than initially specified, usually 25 years. But a lot of the equipment in the plant must be upgraded or replaced when equipment becomes obsolete. Parts or support are no longer available on the market. New equipment and solutions have significantly better performance than that of the original design, or if the legislation changes and dictates that the plant must be upgraded. And a way to extend the lifetime of traditional coal or oil-fired plant is to change into less CO2 emitting fuels to bridge the gap until full implementation of renewables. For instance, natural gas or biomass. Just as an example, natural gas will emit around half the amount of CO2 compared to fuel oil or hard coal, especially. BWSC undertakes re-engineering, supply, installation, and commissioning of, among other things, plant control systems, DCS, upgrade and software and hardware, obsolete electrical equipment, high voltage, medium and low voltage, and DC systems, generator excitation systems, boiler pressure parts, furnace grade, fuel, slag, and ash handling equipment, fuel conversion from, for instance, coal or oil to gas or biomass, upgrade of flue gas treatment systems. To get started and to keep an eye on your plant, make condition surveys and assessments. You can do it yourself, but in general, it's a good idea as a long-term strategy for the power plant to make thorough technical assessments to get new eyes on the plant from a third party, meaning that BWSC can provide these plant surveys to determine current asset condition, benchmark against industry standards, estimate remaining lifespan of equipment for long-term budgeting and planning, provide detailed review of the O&M and operation practice procedures compared to KPIs, to identify and describe any potential optimization leading to improved plant overall performance, better fuel economy or energy savings, lifetime extension, replacement of obsolete equipment, reduction of emission and effluents, etc. Such a survey will consist of an on-site inspection, analysis of data, benchmarking up against industry standards, documentation of findings in reports along with cost-benefit analysis and recommendations. The surveys can be tailored to any part of the plant, a general plant condition assessment, or focus on electrical and or automation, boiler condition, efficiency surveys for fuel economy, output, environmental performance, emissions, effluents, waste handling, and as at mishap damage assessment at breakdown, fire, flooding, or at all worn down plants, emergency response, repair, cost estimates, root cause analysis, and support for claims to insurance. So that's the way to start. So now we are at the end, and thank you for your attention. Please keep in touch. You can write to us on the email here, or you can now unmute yourself or write questions on the chat. Yeah. Do we have any questions, comments?
Not on the chat either.
No.
Oh. But then I guess we should say that, of course, one are welcome to send any questions that may pop up having for the people. It doesn't have to be now.
No, you're always welcome to contact us. And this presentation will be circulated to all of you later today. Yes, but then we'll say thank you for your attention. Bye-bye.